Well, so Ray gravitates towards alien worlds. Our next speaker is more attracted to magnets. Very different, diverse. Muralee Murugesu is an University of Ottawa researcher. He studies tiny, high-density magnets. These magnets can be used to build faster, more cost-effective computers. So that's good for all of us because we all use computers. And he's really, in his work, keeping the information revolution moving forward. What matters to him is the question of whether small is the new big for material science, though in talking to him before, small is everything about him right now because he has a 2-month-old baby at home, and so he loves talking about small things. We talked about his child before. I won't ask you to do that now, but congratulations on having your first son. If we could invite Muralee Murugesu to the stage, he will be answering the question, whether small is the new big for materials science.
Thank you, Pia. Good evening. I would like to start this talk by mentioning a nice talk. And if you remarked in the slide, one of them was the Pluto problem that people were putting up billboards saying that size doesn't matter. But actually, in my world, it does. So here I'm going to talk about small matters that matters for us. Okay. So is small is the next new big thing for material science. If I ask you in the audience, is there anyone who doesn't have a smartphone? Please raise your hand. All right. And the same people, I'm going to ask you the same question. Do you own a computer? Or is there anyone who doesn't own a computer? See? That means we are all guilty. We are whether using smartphone or computers, we are using the similar technologies nowadays. So what I'm going to talk about, the effect of the modern society and the amount of energy we are using in an everyday life, when it comes to computers or smartphones, it's hard to quantify. Really, we don't know how much energy we are using. We talk about fossil fuels and we talk about CO2 pollution, but we never think about how much energy we are consuming in everyday life that we in this ever-growing modern technology world. So if you, just to give you an example, this is the new or future $1.2 billion Canadian communication security establishment in Canada. And they are building this brand new building, and it's going to host one of the most powerful, if not the most powerful computer ever built in Canada. And this computer is going to consume electricity equal to what is enough to light the whole Ottawa region. So you can imagine the amount of power a computer can consume in one single day. So what matters now for us is to create new materials that can basically revolutionize what we are already using and consume a lot less power and perform way better. So in this quest, just a memory lane, if you remember, some of you might have used these tape recorders. You know, I'm from the generation I saw the evolution of this, from cheesy tape recorders to, floppy disk that virtually disappeared. And then from there, we have the hard disk technology. In the old days, the hard disks were like 2 gigabytes or 10 gigabytes, and nowadays we are talking about terabytes. And then these came along in the early 90s. From there, we can get smaller and smaller memory storage devices. This is a small key. We can already store a lot of information in simple memory key. And now we are getting into these solid-state devices. Basically, these are hard disks as well, but in a slightly different technology. The question I'm asking is, what is next? So if we are going to create devices that are going to be better performing, basically the future matters now. We are creating material that's going to impact in the future. So in this quest, basically what my research group is interested in, creating materials that can store information. That means store memory storage devices, hard disk technology. We can simply think the storing as a simple binary unit. That's all computers are working at. We can use this as an interrupter or the switch, light switch, whether you can store information in a state 1 or 0. So these are information storage. But in reality, a computer stores its information in a memory such a way that all the spins are aligned in a certain way. This will be equal 1, and the other information is aligned in a different direction. So this is what we are storing. So in order to store that, if you look at a computer hard disk, you have these magnetic domains. These are quite large, and these contain hundreds of metal ions. In these metal ions, you can only store one information. That means each these domain can whether store 1 or 0. So in order to create high density storage, you need to make these domains smaller. So you can make material smaller and smaller dimension that you can make these tiny domains. But actually, there is a law which predicts that as soon as you get certain limits, they will reform much larger domain, and therefore you will lose your information. So in order to overcome this problem, we have to really tackle this problem in a different way. This is called the top-down approach. That means you're cutting down into smaller pieces. What we are envisioning is bottom-up approach. That means we are building molecules. These molecules are atomic scale. That means atom level. Each one of them can represent hundreds of these molecules can be stored in the same size area. So we can store a lot more information in a small region. So we call them nanomagnets because they are in nanoscale dimension. As I said initially, size matters in this case. So imagine you have an atomic scale technology. You can see today's technology shown here. We can envision storing this much of information in one single device. For example, this is a cartoon version of it, but actually in reality we can perform or create devices 100,000 times better performing and consuming a lot less energy. So the goal is to create faster, cheaper. Everybody wants to get cheaper electronics, that's for sure, and also energy efficient so that we don't consume or we don't continue to consume as much as energy what we are doing now. Therefore, we believe the research matters. This is the research group in my group, and this is the University of Ottawa. My lab is situated, and we are funded through this funding agency, and therefore, we strongly believe the research matters, and today's technology will revolutionize tomorrow. Day life. Thank you.